My name is Marlon from GeoSphere, Austria. My talk today is about how we compare the affordability of heating and cooling systems across different European countries. I will be presenting the methodology behind this composite indicator that we have built for this purpose, together with some results. What's in the agenda for my talk today? First, I will give you a very brief introduction to the GeoBOOST project. Then I will zoom in a little bit on one of our deliverables, this deliverable 4.2, which is about the financial frameworks around geothermal heat pumps. Inside this deliverable is where the affordability analysis that I will be focusing on today sits. And finally, I would like to share some related works that we've done in case you are interested. So now let me tell you a little bit about the project. The GeoBOOST stands for Boosting Geothermal Heat Pumps to Mainstream Cost-Effective and Efficient Renewable Heating and Cooling in Buildings. The consortium is formed by these countries that you can see in the picture on the right-hand side, and it has 9 partners in total. You can see their logos here as well. And with regards to the goals of the project, we have 5 goals. First is to improve data collection and harmonization practices for geothermal heat pump installations, to build toolkits for life cycle cost analysis, affordability evaluation, and business models, to foster regulatory harmonization, and to increase awareness of the geothermal heat pump advantages. And finally, the project also invests in education and training, because as you know, like skills and knowledge are also key if we want to scale up shallow geothermal systems. My presentation mainly sits inside the bullet point 2, as you can see here, and Javiera will cover mostly the objective number 3, and Rick will address objective number 5 today. Okay, so this is the deliverable where today's presentation comes from. It has 3 objectives: to review national subsidy schemes for distributed renewables with a focus on geothermal solutions. We also formulated policy recommendations to address financial obstacles to adoption of geothermal systems. And we also developed a new metric to evaluate the affordability of geothermal heat pump systems against other technologies. That's where the so-called affordability score comes from, which I will keep referring to my presentation today. So what's our motivation to build a new metric? I can tell you that available metrics like net present value, the payback or return of investments are of course very useful, but they mostly focus on direct costs. They do not capture, for example, macro socioeconomic context in which a household lives in. Stakeholders can really benefit from a comparative multi-country view. They need to know, for example, which technologies look more affordable if we do comparisons on a like-for-like basis, and how does that may change by building types in national contexts. So to support that, we are proposing this composite indicator, so-called affordability score, for specifically developed for comparing different heating and cooling systems. As we will see later, the basic idea is to aggregate a bunch of different factors that influence affordability into something that's quite intuitive to make direct comparisons. Here is the scope of the score in a bit more detail. We are including seven system types, 2 types of geothermal heat pump systems, closed and open loop, air source heat pumps, 3 types of boilers, gas, oil, and pellets, and district heating. We cover 4 building types from single family to large scale tertiary. And we also apply the approach to 7 countries like Austria, Germany, the Netherlands, Ireland, Poland, Spain, and Sweden. In terms of service, we look at both heating and cooling for all technologies. That's a very important detail I want to emphasize. However, the boilers and district heating in our comparisons cannot provide cooling, so we also add an equivalent cooling solution for these technologies in order to make these so-called like-for-like comparisons. So how do we really measure affordability after all? We start by defining a set of affordability factors here on the left of this slide. This includes techno-economic indicators such as the capital expenditure, CapEx, operational expenditure, OpEx, the levelized cost of energy, LCOE, the electricity to gas price ratio, in addition to 4 macroeconomic variables: the median income, employment rate, GDP per capita, and a proxy for inflation, which is the harmonized index of consumer prices. So next, we did an expert survey with the project members to derive the weights for each of those factors. Then we collected the corresponding data for each country and building type. After that came the data preparation phase, which is based on 2 subtasks. First, all euro values were divided by the so-called price level indices so that the monetary values are fully comparable across countries, giving differences in purchasing power. Second, because like the factor data have different units and ranges, we apply the min-max transformation to have everything on the same scale. After that, we took a weighted sum of these normalized factors to compute the affordability score. And all scores then are provided on a common 0 to 100 scale, where a higher number then means more affordable. And rather than pretending that all inputs do not come with inherent uncertainties, we also implemented a Monte Carlo engine that randomly perturbs both the factor data and the weights within plausible ranges. So doing so then gives us not just single point estimates, but also a distribution of scores. And from this distribution of scores, we report the means and the 95 uncertainty intervals. Here on the right-hand side, you can see the mean weights that were derived from our survey. The energy cost factors dominate. LCOE, as you can see, has the highest weight, followed by the electricity to gas price ratio, and then CapEx and OpEx. The macroeconomic variables still matter, but each of them carries a smaller share of the total weight. The error bars in this figure show the spread across the experts in the project. So you can realize that there was some disagreement, but the order of importance is fairly consistent here. On the left, I show you the data sources. The main cost factors, LCOE, CapEx, and OpEx, come from another deliverable, the project, and the remaining data were taken from Eurostat. And the calculations are done by considering the year 2023. So I would like to give you a bit more details about the CapEx, OpEx, and LCOE that were taken from a previous GeoBOOST deliverable. In this deliverable, the our partners from Rototech have created a life cycle cost analysis tool based on Excel. And this methodology is very comprehensive. It includes a wide range of costs over the lifetime of the technology. You can see here on my slide that it covers from the initial investment up to decommissioning, including the residual values of the assets as well. And one of the key features of this tool is what we are calling the country preset. Essentially, the country preset holds a predefined sets of inputs for each GeoBOOST country, including, for example, the load profile based on typical meteorological year to get heating and cooling degree days, in addition to domestic hot water statistics. It includes also technology-specific cost curves, drilling costs, climate adjust performance factors for the heat pumps, and specifically for the borehole heat exchangers, earth energy design simulations have been performed for 3 ground thermal conductivities between 2 and 4. And for our purposes here, we assumed a value of 3 for all countries. In addition, we also considered a discount rate of 3.5%, an analysis period of 25 years, and a supply temperature of 55 degrees Celsius, which is conservative for heat pumps. The boilers are assumed to have an efficiency of 92%, and we also incorporated the residual values where the lifetimes exceed the analysis period, for example, for the ground loops that last much longer than that. And as I already mentioned before, all technologies were costed for heating and cooling. Just as a side note, the whole code behind our analysis is already living in this GitLab repository on the server of our institution, and we'll make everything open access, so anyone interested will be able to fully reproduce the results or build upon our work if you wish so. All right, let's move on to the results now. This figure shows the affordability scores for single family homes in the 7 countries. The first thing to realize here is that in almost all countries, the 2 geothermal options are right at the top of the range, followed closely by the air source heat pumps. The error bars in these figures are the 95% uncertainty intervals from the Monte Carlo simulations I've just explained. And you can see here that even with the uncertainty taken into account, the ranking is fairly robust across the countries. There are some cases where the intervals overlap to a great extent, so we recommend treating these differences as more indicative rather than definitive. Poland, I would like to draw some attention to Poland here as the less affordable, but this is when we compare against the other countries. And this is explained by the purchasing power adjustment I mentioned before, which in the end acts to lower the scores for Poland. However, when we look at what's happening inside Poland, even there, you can realize that the heat pumps, and in this case also district heating, are leading. And a note on Germany as well. Germany is the only exception where, in fact, a combustion option leads the affordability ranking, in this case, pellets. We had a look at the data, and the 2 main drivers can explain this result. First of all, Germany has one of the most expensive electricity prices in Europe, having the highest price ratio to gas in our sample of 3.4 in 2023. And the other factor, the other driver is the drilling costs, which are about 110 euro per meter in Germany. When in Sweden, for example, it's only around 30 euro per meter. Okay, on the previous slide, we looked at single family homes. Now in this figure here, I am showing you the affordability score averaged over all building types. And I've also added this overall across countries panel on the top left, which further shows the average across the 7 countries. The big message here I would like to emphasize is that the pattern hardly changes. The geothermal options still come out on top, followed by the air source heat pumps. And gas and oil boilers normally stay at the bottom of the ranking. So to wrap up, we have developed a composite indicator that measures multiple factors into a 0 to 100 benchmark for making direct comparisons of the affordability of heating and cooling systems across countries and building types. The score combines direct costs, energy price structure, and macro context. I would like to emphasize that the score is not an absolute measure of cost effectiveness, and it is not intended to replace project-specific assessments. The best use of it is comparative. The methodology is transparent and reproducible. You will be able to access everything that we have done in the future. A link will be provided in the deliverable. And as I mentioned before, the methodology can also be tested for other scenarios, for example, as the energy prices evolve. And we are also finishing some calculations that include, for example, the financial support from governments to test how grants would change the rankings of the technologies, for example. And I would like to finish with the main conclusion of this analysis, that the geothermal heat pumps sit at the top of the affordability ranking in our comparison, with the benefit of providing both heating and cooling intrinsically. And this is one of the references, further reference I would like to give you before finishing my presentation. This is another GeoBOOST deliverable that we have done, in this case dealing with the challenge of improving data collection, monitoring, and standardization practices for geothermal heat pump installations across Europe. You can go to the project website if you want to read the full report. And we also published a paper recently about the diffusion of groundwater heat pumps in Austria over 33 years. If you are interested in the details, the link for this paper is here as well. Okay, I will stop here. Thank you very much for your attention. If you'd like to follow up, feel free to contact me. And thanks again to the organizers for having me today.
So, okay, good afternoon, everyone. As already was mentioned, my name is Javiera Chocobar. I am from the Technical University of Munich, and I am very happy to be here representing the GeoBOOST project. So today I will present one of the GeoBOOST results from the Work Package 3, which focuses on the regulatory and legislative aspect that influence the deployment of geothermal heat pumps across Europe. So let's start with a bit of context, which will help us to in the end answer the question, why do we need a framework for shallow geothermal deployment in Europe? So as we all know, the climate crisis demands a drastic reduction of emission, and the decarbonization of systems has become a top priority, especially in urban areas where most energy demand is concentrated. Also, across Europe, the need for sustainable heating and cooling is increasing rapidly, while at the same time, the energy security has become a major concern again. So in this context, accelerating the adoption of cost-effective and energy efficiency renewable heating and cooling technology in the end will be key to achieve the European climate and energy goals. So there is where, under this scenario, where geothermal heat pumps come in, as they provide a reliable, low carbon, and highly efficient solution for heating and cooling. However, the adoption remains uneven across the region, and this is because there are still important barriers slowing down the deployment, such as the licenses, long and complex licensing procedures, the lack of coordinated subsurface thermal planning, and limited integration of geothermal energy into spatial urban planning framework. And these barriers are not purely technical problems, they are also regulatory and administrative hurdles. So within GeoBOOST, Work Package 3 focuses precisely on this challenge to understand how planning, integration, and licenses can work together, and to propose practical tools to support authorities and developers across Europe. To address the challenge, the way that we didn't look them in isolation. Instead, we approached them in an interconnected perspective, linking technical, regulatory, and planning aspects. This perspective allows us to design solutions that are practical, harmonized, and also adaptable to different national contexts. Our methodology combines a legal and technical analysis across the 8 countries, so the GeoBOOST countries: Austria, Belgium, Germany, Ireland, the Netherlands, Poland, Spain, and Sweden. We examined national regulatory frameworks, identified gaps and inconsistencies, and developed concepts and guidance for improvement. From this, we created 3 toolkits, each addressing one of the mentioned barriers in the deployment for geothermal shallow energy systems. So let's start with the first toolkit. In this first toolkit, we focuses on the thermal interference and optimizing planning. In it is established a common terminology for thermal interference, highlighted the links between environmental and energy regulation, and also provide legal and technical basis for assessment conflicts between systems. We also propose in it 6 technical parameters categories that include in the end temperature, distance, system side, subsurface condition, seasonal performance and extraction, and discharge rate to help planning authorities evaluate new installations. So this framework provides the regulatory and technical foundation needed for legislative clarity, and also ensures that permitting processes are based on consistent risk-based criteria and supporting the long-term sustainability use of shallow geothermal resource. The second toolkit, it's a guideline for integrating geothermal heat pump into spatial urban planning. And in it, we propose a workflow for integrating geothermal into regional and local planning instruments. This workflow consists in 6 steps: heating and cooling demand assessment, actual state of energy supplied, analyze, potential analyze, identify potential priority areas, define measures and implementations, and monitoring. And also, it addresses governance challenges, particularly the lack of the link between energy land use and environmental planning. By embedding geothermal energy into spatial area planning, authority can move from a reactive to a proactive approach, anticipating opportunities and challenges early in this process. So this in turn create a more stable and predictable environment for both planners and developers. The last toolkit, it's a guideline for reducing licenses barriers, and this focuses on simplifying licenses procedures. In it, we propose concrete measures to streamline licenses at local and European level. These measures include process simplification through risk-based licensing approach, standardization of form and criteria, digitalization and integration of application systems for creating transparency, access to information and technical assistance, training and certification for staff involvement and licenses, coordination mechanisms between authorities on energy, water, or environmental. And this is in the case where multiple permits are involved in the licenses process. Also, it is include environmental criteria and monitoring, and subsurface planning to prevent conflicts, especially in urban areas. So together, these measures aim to make licensing faster, clearly, and more predictable for authorities and users. But in this guideline, work doesn't stop at recommendation. It is also addresses how to implement and monitor the measures over time. The proposed strategy includes gradual implementation, regular performance evaluation, including indicators like average processing time or numbers of approved applications, feedback loops between local, regional, and national level, and a data-driven approach for continuous improvement. This acknowledge that regulatory frameworks are not static. This must evolve through monitoring, adaptation, and feedback to sustainable promote geothermal energy. In conclusion, addressing regulatory and legislative barriers is not only about simplifying process, it's about building trust, efficiency, and long-term stability. Through Work Package 3, GeoBOOST delivered 3 comprehensive regulatory toolkits that together form the foundation for scaling up geothermal heat pumps in Europe. They connect technical understanding with planning and regulations, ensuring that the sector can grow up in a safe, transparent, and harmonious way. The next step is to support member states in adapting these tools to their national context, and by doing so, unlock the full potential of sustainable heating and cooling. So thanks for your attention, and I will wait for your questions.
So, good afternoon, everybody. My name is Rick Pasquale from GeoServe. Very pleased to be with you here today to talk some more about the GeoBOOST project, along with my 2 other colleagues. I'd like to first of all acknowledge the the work of our task leader on this new online shallow geothermal energy course. So Hossein Javadi from the Universitat Politecnica of Valencia, who has been the main driver behind setting this MOOC up with the cooperation of all the project partners. So today I will briefly cover some of these points during the course of my talk. I won't spend too much time on the objectives of the project because you've already heard from Marlon in relation to these. I will spend some time talking about the Mass Open Online course, the MOOC, as it's known for short, and would like to outline a little bit what the course content is, who the target audience are, and why this course was, originally sort of set up as part of this project. Then the last part of the talk will just be a brief overview of the EDX platform, which is the platform on which the course is taught, just to show you some screenshots on how you register and go about actually starting the course. And then very, very briefly, some initial course statistics from October to present. So in terms of the objectives, I don't want to cover this again. You've heard these objectives from my colleague Marlon earlier on, but just to highlight that this presentation really touches on key objective number 5, which is growing and upskilling the workforce. So as part of developing this project and the GeoBOOST concept, it was clear that additional growth in workforce is needed in order to support the geo-boosting that will happen as a result of the outcomes of the project, and more importantly, that upskilling the workforce was by providing training and education is one of the key aspects that needs to be addressed. So in that context, then, what is the MOOC? So the European Modular Massive Open Online Course. It is basically a course that was developed to provide a standardized, high quality training platform that can be adapted to specific local needs and stakeholders. And there have been previous, let's say, versions of European-based shallow geothermal skills training programs in the past, but they have never been quite as comprehensive as the MOOC platform that has been developed as part of the GeoBOOST project. So the online course started on the 1st of October. Broadly, there are different modules, which I will talk a little bit more about in the next few slides. But the broad course duration is 6 weeks, and it's an online format, which means the course can be taken in different bits and sections. It doesn't have to be followed all in the one go, but I will speak a little more about the actual structure of the course itself later on. The language is in English, and the course is obviously free for the initial, let's say, part of the training, but there is an opportunity to obtain a certification at the end of the course at quite a small cost. So in this slide here, really, this both sets the context on the left-hand side and explains a little bit the content on the right-hand side. So the reason why the MOOC was set up in the first place was to allow for training and education and awareness raising to happen, let's say, across a broad range of different stakeholders. And those stakeholders you'll see are listed there under recommended. And these may be stakeholders such as drillers or policymakers or decision makers, or indeed professionals who are active in the industry who would be normally trained in their specialized skills at different levels for particular aspects that are related to geothermal heat pumps, but are not, let's say, necessarily holistic when it comes to heat pumps. And on the right-hand side, you can see that the course content covers a wide range of topics. And so with the spirit of trying to reach out to as many professional entry-level learners or any form really of technically inclined participants, it was important for this course platform to be able to deliver some awareness, knowledge and education on a number of different key topics. So you can see there that there are basics and fundamentals of ground source heat pumps. There are modules relating to energy efficiency and energy assessment. There are other modules including understanding the subsurface and drilling methods, all the way down to ones that are probably more specific to decision makers and planners that relate to legal frameworks, environmental considerations, and so on and so forth. So you can see the scope is really quite broad. And the key takeaway message from the slide is that the course has been structured and developed with the background of established certification schemes and courses in many different European countries. So we have taken basically the best across Europe to develop something that is transferable to all different EU markets. So there are 5 modules in total. You can see the broad MOOC content there. So module 1 is a general introduction. Module 2 relates specifically to energy efficiency in buildings. Module 3 is borehole heat exchangers or closed loop geothermal heat pumps. Module 4 is for groundwater heat exchangers, and module 5 is for horizontal collectors. And you can see from the slide deck there are a number of sub-modules under each one. And the course content, of course, for all of these is available to everybody who is registered and who takes the course in the first place. So these are the general headings. I am not going to have time to spend a lot of this webinar describing the content, but you can see module 1, module 2, module 3 and 5 in the table contain different sub-modules with different topics. So the fundamentals, module 1 is the longest. It contains a little bit of everything. The idea behind it is to give a background to the technologies, to the deployment, and to the permitting requirements. And then the other modules are a little bit more specific. So like module 2, for example, has examples of how you size, how you integrate, and how you design geothermal heat pumps for particular buildings. But it also has a series of sub-modules on different case studies showing energy efficient applications of geothermal heat pumps in buildings. So the structure, let's say, of the course, it's basically a video, it's a lecture-based approach that is done online. And there are then reading materials, so supporting documents to the actual video lectures, which are accessible to all of the participants. And then at the end of each module, there are interactive activities, and those activities include quizzes. They include true or false questions and matching exercises. And one important thing to note is that there is an exam at the end of each module, which requires, well, the requirement is to have up to 80% across all the modules to pass the course. So the MOOC is typically chronological. It takes overall 6 weeks to complete, or that is the time you have to complete the course on the platform. And we would recommend a sort of a period of about 1 to 2 weeks per module, depending on which one it is. And there is some level of support through a Q&A system between the course participants and knowledge sharing through the experts that have contributed to putting the course together. So now just a few short slides to bring you through what the platform looks like. So if you use either the button on the bottom of the slide is actually hyperlinked to the location, and I will share the link to the course in the chat in a minute. You will be brought to the first registration window of the EDX platform. So this is a generic registration for the online platform and not necessarily for the course itself. So you can complete your details in there. And then the next thing that will appear is effectively the opening session and course enrollment, if you want, for the geothermal energy skills development and training across the EU, which is the one that you want to be looking out for. Once you have enrolled for that, you will then be taken to the first, you'll see now the platform will show you that my courses will be included as part of your EDX registration, and you can basically start your course profile. So once you actually open the course itself, you will see basically a welcome. There is a welcome module to explain what the course is about and how the platform works. And then you can see that each individual module is listed and the various sub-modules underneath. So here's an example of module 1. And you'll note at the end of module 1, there is a final evaluation for part 1, which is basically one of the exams at the end of that module. So effectively, if you click Start Course at that point in time, you will be brought into the Welcome section and then straight into Module 1. And you can stop the course and start the course at your leisure as you're going along. So this is just a very brief screenshot of what the video training looks like. It's one of the videos from Module 1. So you will get materials to support PDF materials and reports to support the content in the videos. But then at the end, there are a few critical things that you need to consider. So first of all, please remember that you can obtain a certificate, but the certificate at the end is not free. There is a small cost associated with it. And I'd like to just point out a few other practical things. You need to make sure that when you have pressed the start course period, you then have a ticking clock of 6 weeks for you to complete the course after you've pressed start the course. So if you don't complete the course in those 6 weeks, unfortunately, your changes or what you have done, the work that you have done up to that point will not be saved. You will have to start the course again, basically. So there is a verification upgrade deadline, and that's basically the upgrade to get your certificates. And then there is a course end date that you can see at the bottom on the right hand side of your own personal panel. So just keep this in mind, that once you press the start the course menu button, sorry, you need to try and complete the course within 6 weeks. So briefly, some statistics. Since the course opened on the 1st of October, there have been 365 enrollments, and that's up to about 2 weeks ago, with participants from 64 different countries and regions. And you can see the split there in terms of the actual candidates. Quite a low percentage of sort of high school diploma or less, with stronger, much stronger percentage of more advanced degrees. So masters, PhDs or postdocs, or at least third level graduates were taking the course in order to gain certification. So this is all I have for you today. There is a QR code on the screen, and the enroll button is hyperlinked. And in a moment, I will paste the link to take you to the EDX platform in the chat. Thank you very much.